As Sir Isaac Newton studied moving objects and noticed the patterns, he developed something that we call the second law equation. You've kind of been using this equation already in the previous problems. However, we're going to learn a slightly different way to write it, and it's the form that we're going to use for the rest of the year. In equations, direct variables go on top. That means that we multiply. And inverse variables go on the bottom. That just means we divide. Now, in this lab, we multiplied by force, so it goes on top, and we divide by mass. It goes on the bottom. And doing this, we were able to predict the acceleration of the object. So what you are looking at, this equation, is called the second law equation. I don't know about you, but I don't like fractions, and so we usually don't write it in this form. What I'm going to do is get rid of the fraction by multiplying by m. But the number one rule of algebra says that if I do something on the left side, I have to do it on the right side. And so what we have now is the equation F equals ma. This is the form you will see if you look in a textbook, and this equation is called Newton's second law equation. We're going to be using it a lot next week. Luckily, it's a very short equation, and so it's easy to memorize. Let's look for a moment at the units inside of this equation. Forces are measured in something called newtons. Mass is measured in kilograms, and acceleration is meters per second per second. By looking at this equation, I can see that the newton is actually equivalent to a kilogram meter per second per second. So when you tell someone that gravity is when you tell someone that a force is 10 newtons, what you're really saying is 10 kilogram meters per second per second. Now, nobody likes to say the full unit because kilogram meter per second takes a long time to say and to write. And so that's why we gave it a new name. And basically, these units, when you put them together, have been renamed the Newton in honor of Sir Isaac Newton. And we will be using the Newton for the rest of the year. You just need to be aware that there are standard units inside of the Newton. And this is why it's so important when we do class labs that we measure things using kilograms, meters, and seconds rather than other units. Let's also take a moment to look at the weight equation. When I gave you the weight equation last week, it was just kind of a magical equation that came out of thin air, but I'm going to show you now where it came from for reals. So we start with the second law, F equals ma, and if we're dealing with weight, then the force is going to be the force of gravity. Mother Earth reaches up with her tendrils and pulls you down. M is going to be the mass of the object, and A is going to be the acceleration of gravity. Now, we can use different letters to abbreviate these. We learned last time that the force of gravity is abbreviated with the letter W for weight. Mass we're going to keep with the letter M. And then the acceleration of gravity is such an important number that it's given its own abbreviation. We use a lowercase g. If you go to the amusement park and a ride tells you that it is 5 Gs, what it really means is the acceleration is 5 times the acceleration of gravity. Notice, as I put these letters back together, that we formed the weight equation. So the weight equation is actually just an application of Newton's second law. Now you know where it comes from, and so as we use it for the rest of the year, it will no longer feel like a magic equation. We're going to talk now about the direction a force points, because it makes a big difference whether you push up, down, left, or right. They will each have a different impact on what the object does. This is because force and acceleration are both vectors. This is just a fancy way of saying that they have direction. In other words, we can draw force and acceleration using an arrow. You also need to remember that inertia wants the object to continue doing what it was already doing. You'll see some examples of how this influences the behavior of a moving object. As I show you these pictures, there are places in your notes where you can sketch these diagrams yourself, as well as the conclusions that we come to. So make sure that you use that space as I'm talking you through these examples. First, we're going to look at something called parallel vectors. Imagine that you are driving your car, and your car was already moving to the east. Okay, I can draw this in the picture just by making an arrow that points to the right. Now, while your car is moving, you push it to the east. Now, how would you do this on a real car? I don't know. Let's pretend that this is like a Flintstones car, so there's a hole in the bottom, and you can put your feet down onto the road and push the car forward. Notice that the new force is pointing in the same direction as the initial speed. This is why we say it's a parallel system, because those arrows are parallel to each other. Common sense tells you what's going to happen next. The car is going to speed up. It will move faster because you gave it an extra push. So, what you need to remember is that parallel forces will increase the speed of the object. And when I say parallel, I'm talking about the original motion of the car is parallel to the applied force. Let's look at a different example, anti-parallel. Once again, your car was already moving to the east. We can draw this with a forward arrow. But this time, we're going to push the car to the west. If this was a Flintstone car and it had a hole in the bottom, this means you would put your feet down on the road and you would push backward. You're pushing the wrong way. Notice when we draw this, the new force arrow is pointing opposite to the initial speed. We call this anti-parallel. It means they're exactly opposite of each other. Now, common sense tells you that your car is going to slow down. In general, if a force is anti-parallel to the current velocity, then the object will lose speed. The last scenario is perpendicular. Once again, your car is already moving to the east. We can draw this with a forward arrow. This time, we're going to push your car to the north. When we draw this, that means the new force is pointing upward. And so the red arrow and the blue arrow form a 90-degree angle. They make a perfect corner with each other. If this happens, your car won't speed up and it won't slow down. So what's the other option? common sense says that our car is going to turn. It's going to deflect towards the north. As a general rule, if an applied force is perpendicular to the current speed, then the object will turn. Remember that turning counts as a form of acceleration, even if the number of the speed hasn't changed. We need to talk now about the difference between an instant force and a continuous force. An instantaneous force is a force that is very short-lived. It's applied briefly and then it disappears. If an object experiences an instantaneous unbalanced force, then it will accelerate briefly and then restabilize, meaning that the velocity will change, but then the new velocity will remain constant in the future. There's a place in your notes for you to draw the following diagram, so make sure as I talk about this that you're sketching the picture. Imagine that you have a spaceship that's gliding sideways when it is struck by a small meteor. Now, that just means that a small rock in space hits the side of the spaceship. This is a very brief collision. It lasts for 1 second and then it's over. Well, what's going to happen now? Because the force was perpendicular to the speed of the ship, it's going to make the ship turn. So our new speed will be angled. Notice that because of inertia, the ship does continue to move forward, but because of the impact, it also moves downward. And when we put this together, we get a downward angle. Now, the new speed of the ship is constant, meaning that it will continue to move in the new direction at a constant speed because the force has ended and there will be no more acceleration. On the other hand, a continuous force is a force that keeps going and going and going. You don't turn it off. It lasts for a long time. If an object experiences a continuous unbalanced force, then it will keep accelerating. This is not like a one-time deflection. It's going to accelerate and accelerate and accelerate forever unless you turn the force off. So our example, you have a spaceship that is gliding sideways when it activates its thrusters, and it leaves the thrusters on. So there is now a downward force pushing on the ship, and it lasts for a long time. What's going to happen, because the vectors are perpendicular, it's going to turn the spaceship, but this time we get a curve because the ship continues to accelerate because the thrusters keep pushing it more and more and more. Remember, we learned that curves are associated with acceleration, and so the path will continue to curve until the thrusters are turned off. The last thing we're going to talk about today is how the second law interacts with the independence principle. Basically, because of independence, we must deal with the x and y forces separately. That means that when you use Newton's law, you're going to use it in both the x dimension and the y dimension. The net horizontal force will only affect the horizontal acceleration. When we use Newton's second law equation, we show this by putting little x's into the equation. This just means the net force in the x dimension equals mass times acceleration in the x dimension. So we're only looking at the horizontal motion of the object. Similarly, the net vertical force only affects the vertical acceleration. We show this in the equation by putting in little y's. If you have a force diagram and you're solving for acceleration, you actually have to get two answers. You get your horizontal acceleration and your vertical acceleration. It is possible to have both kinds of acceleration at the same time, but you'll solve for each number separately. There is one more page in your notes packet, but we are going to go over that next week when I come back. And so this is the end of today's lecture. If there's a lot of time left in class, then just find something quiet to work on, and I will see you next week when I get back from New Zealand.